Okay, hello. I guess this is the clicker. Hello, hi everyone. Let's see. I'll wait for the slides to go. Yeah, so I want to tell you about Stwo, but first I'll tell you a little bit about what came before Stwo. So, a tale of two provers. Our first prover, oh wait, I'll go back and say. My name is Ben-Sasson. I'm co-founder and CEO of StarkWare. StarkWare has a team of about almost 200 folks, and we build Starks for production systems. So our first prover, which has been running in production for 4 years, called Stwo, works over a 252-bit field. And there's a new prover that will be the focus of the talk that is running over a 31-bit field. And I want to tell you about it because we really love it, and I think you're going to love it as well. So before we get to Stwo, I'll just say that Stwo, we're very happy with its performance right now because it can support very great scale. It's already saved Ethereum users over $500 million and settled over $1.2 trillion over its life. And in fact, all of our StarkNet systems are currently already running over Stwo and running very well, meaning, we're now in our next upgrade, which is coming out later this month. We can support TPS of upwards of 250, maybe even 300. And by the end of the year, this will go closer to 1,000. All of this uses Stwo. And there are other nice things that are going to come in this upcoming upgrade, again, supported by Stwo. For instance, you can do Groth 16 verification, 100 or more per block on StarkNet. So if you like layer 2s and you want to program stuff and you want, let's say, privacy-preserving layer 3s, things like Zcash style things, you can do them today on StarkNet. So all of this is supported by Stwo, which begs the question of, why would we want Stwo? I want to tell you about 4 aspects of Stwo. The connection to community, because it's a collaborative, open source project, and I would like to invite all of you to be involved in it. I want to tell you about the very fast timeline in which it's arriving. Then I want to tell you about the really exciting stuff, which is the innovations that go into there, the math and other stuff, and how fast it is. Okay, so.
And then eventually I got to 120 hashes per second, and I was really happy. And then I asked some lovely StarkWare people, okay, how much do you guys get? And they told me 500,000. So, that definitely was interesting, right?
So this was Vitalik's reaction and the Ethereum Foundation's reaction to the fact that the Stwo prover can show a throughput of upwards of 500,000 hashes, Poseidon hashes, proving 500,000 Poseidon hashes per second on a quad core. And on stronger machines, it goes over 1.2 million hashes per second. And I'll show you some numbers, and we'll dive into the details of what goes on there, which is probably 100x better than what the world has known before. So Stwo is a collaborative project, which means it is open source, and it has a templatized backend that's supportable on multiple infrastructures and hardware settings like SIMD, GPUs, WASM, FPGA. So if you're interested in collaborating, you can either by yourself or talk to us and get involved in implementing or improving one of these backends. We already have a number of ongoing initiatives with external teams to build things like, first of all, we're talking with the Ethereum Foundation researchers about whether this can impact the roadmap of Ethereum, because now you can do things like signature aggregation and, sub-second data availability, finality using Stwo. So you can rethink the possibilities for Ethereum itself. We have a number of teams building GPU backends already. We have teams building a Stwo verifier in Cairo, which is the Stark-friendly programming language that powers StarkNet. And we have a project about Stwo verifier on Bitcoin, because we're also going to put Stwo on Bitcoin within 6 months. We're going to put StarkNet on Bitcoin within 6 months of having OpCat adopted, if it's adopted. And this will be thanks to Stwo, and it will be done using Stwo, and we have already shown, together with Wei-King Chen and L2 Iterative, how this can be done on Signet Bitcoin signet that has opcat turned on. So if you want to collaborate more, there are a bunch of things you can do. For instance, right now the Starks we're building are not ZK, but you can turn them into ZK Starks, relatively well-known and not too hard project, but very interesting. You can write specific errors and constraint systems for various virtual machines like RISC-V, RISC-V, EVM, and so on and so forth. We will definitely be adding all of those, but right now our focus is first most on, I'll show you in a minute, on getting Stwo to StarkNet. So all of these projects, if you want to build them, please talk to us. Benchmarking, comparing to other proof systems, building more backends. If you want to be involved, please reach out to us, or we have a table outside, or anyone with a StarkWare shirt, please talk to us. There's a lot to be done here, and we have actually a bunch of Stwo engineers with us. I see Andrew Milson in the back. If you see all the way to the back, you want to hear how it really works or talk about the code, talk to Andrew, because he knows it. Okay, so let's talk about the very vigorous timeline that we set. We started building Stwo about roughly 1 year ago, and in June, the recording I showed you of Vitalik speaking, that was last month, and it was talking about stuff that the Ethereum Foundation researchers discussed with us in June when we released the benchmark for Poseidon that sort of blew the mind away of many people, including ourselves, the 500,000 hashes proved on a quad core. I'm going to share with you later now our very nice numbers for Blake 2, which is a standard hash that we're releasing today. And I'm also going to share with you initial results on GPU backend. All of these things are going to be, so the Blake 2 is already open sourced and you can use it. The GPU is still in works, but I'm going to show you some initial numbers. In the fall, we're going to first have the air for the Cairo virtual machine, and shortly after we'll add all of the built-ins needed in order to have Stwo performing recursion and operating inside StarkNet. Now, what this means for StarkNet programmers, it means you do not need to change anything. All the contracts and all of the code will be running the same way it's been running today, but we will see faster finality, lower costs, the potential for client-side proving, and a whole bunch of other things. So the main thing here is that you will get a lot of improvement and reduced costs, but without changing anything, and all of this will reach you by March 25. Now I want to tell you a little bit about what is going under the hood with Stwo. So how did it come about? And now I'm going to talk about this very beautiful math breakthrough called Circle Stark. It is joint work of Ulrich Habok from Polygon Labs and Shachar Papini and David Levitt from StarkWare. You can look it up. It's a beautiful piece of math that I'm really excited about. So how did it come about? Well, we want a more efficient Stark than the one that we have, and we want it to be able to run very quickly over commodity CPUs and GPUs. Now, you all know that the basic units of operation on both CPUs and GPUs are 32-bit words. And you may also know that both of them support very fast integer arithmetic. CPUs also support the kind of arithmetic or the kind of operations needed for binary field multiplications, but unfortunately GPUs do not. Which means that if you want something that is very fast on both CPU and GPU, you probably want something that works with 32-bit integer arithmetic. Okay, so this leads us to pick something that fits. It's a prime field that sits inside a 32-bit word. Now, which ones? The one we already all know of and actually love is the one used, for instance, by the RISC-0 team called Baby Bear, that actually has an FFT-friendly subgroup of size 2 to the 27, so you can do a lot of cool stuff with it. But there's an even better field that allows even faster multiplication, roughly 30% faster, and it is called M31 or Mersenne31, and it is the prime number 2 to the power 31 minus 1. And because 2 to the 31 equals 1, this leads to very fast multiplication, and we wanted to use it. The problem is that if you look at the multiplicative subgroup of this field, which is very much necessary for fast Starks, it doesn't have a nice structure. It doesn't have an FFT-friendly structure. So why is the FFT group needed? Well, it's needed both for fast evaluation, low degree extensions, interpolations, which are needed when you're dealing with univariate polynomials. And it's also needed to run the protocol of Fry. So what can we do? We have this field that we would really like to work with because it really is fast, but it doesn't have the needed structure. So here's the multiplicative group of M31, and this is its size. Its prime factors are not very FFT friendly. You would like to see something like 2 to the high power times some small prime. But that's not the case here. Well, we already know, since our work with Dan Carmon, Swastika Party, and David Levy from 2021, that you can find an elliptic curve of the right size and use that to get a group of size, let's say 2 to the 30-ish, and do everything you want. But it's a little bit complicated. You know, the sequence of transitions and the twiddle factors you get are not very pleasant to work with. So the three brilliant, you know, mathematicians and engineers I mentioned earlier, Ulrich, David, and Shachar, suggested using an even simpler curve that we all remember from our days in high school, which is the circle, the set of points such that, you know, if you square them and sum them up, you get 1. And you get 1 modulo the Mersenne prime. So for instance, the point 2 to the 15, 2 to the 15 is one of these points. And this turns out to have a very nice quadratic doubling map, and it's something very convenient to work with. It looks very FFT friendly. So there are some complications. For instance, a line intersects this curve at 2 points, which means that you have to deal, well, you're going to deal with bivariate polynomials as opposed to univariate polynomials. So things could be slightly less efficient, or it seems they might be less efficient. And if you look at the algebraic geometry, there are some complications there as well. You don't get a nice Riemann-Roch space. Luckily, you know, these guys fixed all of those things, so it's safe to use, and it's as efficient as using the good old FFT and Fries. So let's see what are the operations that are needed in terms of the group theory. There's an identity element, which is the point 1, comma 0. Doubling is sort of what you would expect it to be, you know, sort of like angle addition. And the nice thing also about doubling is that if you look at the at doubling and then projecting onto the x coordinate, you will see that there's no dependence on the y coordinate, which is very, very useful and helpful. And also the inverse of every point is just you flip the y coordinate. Okay. Then you have your subgroups and a coset of a subgroup. And if you take a coset of a subgroup in which there are 2 points above every point x, then you get what we call a canonical coset. And what's really nice about it is that you can have these projections onto the x-coordinate that are 2 to 1 projections. And basically, for every point that is projected onto, you have 2 points that are its pre-image. And because of this, and because of the fact that doubling and projection commute, you can actually, and I'm jumping, you know, I'm skipping over a lot of math, you can actually move from these bivariate polynomials immediately to a pair of univariate polynomials with no reduction in efficiency, and you're basically back in the world of good old things like FFTs and Fries with univariate polynomials. So let's talk about what this translates to into in terms of efficiency. So, okay, for those of you who attended, I gave a talk also about like, I think there it was about like Fry versus KZG, or like latest results on Starks. And one part of it that I think led to some contention was, I showed this slide. This slide was a back of the envelope estimate of how in an ideal vectorized world, why are small field Starks better than you know, number theoretic constructions that have MSMs in them? And back then, a year ago, I used this slide. Just, you can focus just on the very bottom that talks about, we estimated that per word of commitment, you would take 35 to 40 clock cycles, and you would take roughly 40x more to do the same thing using an MSM-based KZG. So what we did this time is we actually measured, because now we have Stwo measurements and we used, so let's just, neglect everything else. So now I want to share with you the measurements that we recently did. If you take Stwo M31 and you measure it, compared to the fastest vectorized version of KZG that we are aware of, which comes from the Dalek ECC library. And what you get is a factor of not 40, but 30, because you have 750 clock cycles per word using an MSM-based system, KZG, as opposed to 24.5, which is what we clocked using Stwo. So you get a 30x factor improvement when using small field Starks, which has been something that we advocated for since we founded StarkWare 6 years ago. We knew that this will be the best and fastest thing to use. Now, we already shared this information that using Stwo, you can, on a quad core with AVX 512, you can get 500,000 Poseidon hashes proved per second. And this is better than, for instance, what we could do with eStark over a 64-bit field, which was 10,000 per second. And it's certainly much better than what we can do with Stone, which is a 530 per second. This opens the door to things like sub-second recursion and sub-second state diff proving, which again, this is something that is very much interesting, even for the Ethereum roadmap, because you can do very interesting stuff there to be elaborated upon in different time. It also allows you to put StarkNet on Bitcoin, because Bitcoin works with words that are 32 bits at most, so you really want to work with a Stark that has very few bits in it. What about standard hash functions? So now I want to share with you this information that is new, but it already appears in the GitHub of Stwo, which is what we get for Blake. So for Blake 2, we can prove 22,000, well, almost 23,000 hashes per second using, again, a quad core with AVX 512. We estimate, but we haven't written this down, we estimate that SHA-2s you can get around 17,000 of them. And the best state-of-the-art that I'm aware of prior to this was the Plonky 3 numbers that come from a very powerful machine, right? An M3 Max that give you 2,500. So again, a very noticeable improvement in the number of hashes that you can do. And if you do a back of the envelope estimate for how much time would it take to do a recursive proof, to prove that you verified a Stark. So here are the current numbers, and they're not optimized. You can do much better. So if you use 3-bit grinding and, 30-bit grinding, and you want roughly 120 bits of security, and you make 90 queries, which give you a conjectured security of 120 bits, this leads, according to our current measurements, you're going to need to prove 24,000 Blakes. Well, we can prove 23,000 Blakes per second, which means that within 3 seconds, you can probably get a recursive proof. Now, things get even better because, as we do already today in our stack, we don't use the Blake hash all the way from the bottom to the top. We only use it for the lower layers, and at some point above, we start using something like Poseidon, which again, Poseidon, we can do hundreds of thousands per second. So probably with not a lot of work and optimization, you can get sub-second recursive proofs on a quad core, right, on a very simple laptop. Now, under the hood, what is going on here? So there's also a very nice arithmetization coming from the Stwo team that allows you to use, well, in the Stone system right now, when we want to encode a single Blake, we spend roughly between 70,000 and 100,000 cells. Each cell is a field element, and each field element is actually 252-bit fields. Because of the improvements in arithmetization and the use of things like logups and lookups, Poseidon, has always been around 200, so here it's also 200. But for Blake 2S, the thing that is on GitHub today uses about 7,000 cells. About 4,500 of them are Air Blake cells, and 2,600 of them are related to logup. Here are some initial measurements also. We're revealing this here for the first time from an external team that shows the efficiency, the initial efficiency, not optimized, of using a GPU for various parts. We don't yet have a good end-to-end measurement, for instance, for Poseidon. I hope this will come out in the coming few weeks. But you can see that you get speed-ups of anywhere between, let's say, 5 and 45x faster on the GPU, depending on which part of it is. And again, this is not yet optimized, but you can expect, upwards of 1 million and even more hashes proved per second on commodity GPUs, which is, again, extremely exciting. And again, this is code that will be open sourced and everyone can use it and test it. Now I want to show you a little bit about what is the time breakout of spending, where do we spend, where is the prover spending time, and what can we learn from it? So here you have this pretty, we'll share the slides so you can study them on your own. You can also run some scripts and get these numbers from the open source code. But this is the breakup of the time. Roughly 1/3 of it is related to generating the trace of the Stark. Roughly a little bit over 1/3 is related to generating the constraints and committing to them. And then roughly, something like 1/4 or so is related to doing the logup. And one interesting thing is that the whole fry, everything about the fry is like 1%. Like takes very little time. It's just 1% is related to using the Fry protocol. Now, what can we learn from this? Okay, first of all, how much can this be improved on? So assuming we have the optimal implementation, which we don't have, but if you fix the following two things. If you're going to fix the fact that you're working over M31, and you're going to fix a specific arithmetization, let's assume that this is the very best arithmetization possible for the problem, then this already implies that you cannot do more than 10x better than what we have. Why? Because 10% is just spent on filling out the initial trace before doing any polynomial operations. Just writing down the values that you're using in your arithmetization takes 1/10 of the time we're spending right now. So even if everything else is optimized and it takes 0 time, you've only sped up the system by 10x, which is considerable, but I'm just saying it shows that you can't do a lot more. Now, if you are going to do anything between either an AIR or a GKR, and you're going to use an interactive protocol for basically doing a permutation argument, then actually you probably can't do better than 2.5x over what we have here. Why? Because these 3 red parts, again, they involve no low degree extension, no Merkle commitments, nothing of that sort. This is just writing down the values, the algebraic values that are needed in order to do all of the other stuff. And this already takes upwards of 40% or around 40% of the time. So you can at most, even if everything else were optimized, you can at most do 2.5 times better. Of course, you can, optimize the code more and then maybe things will look different. But I'm saying it seems that as long as you're working over a 32-bit field and using a specific arithmetization, this is pretty darn efficient. Another thing that is interesting is if you look at the time spent on FFTs and on Merkle commitments, they're roughly almost the same, or rather everything related to low degree extension, which is both an inverse FFT and an FFT, this takes roughly 2x the time that it takes to do the Merkle commitment. That's the current state of it. So hashing is very, very efficient, and so is FFTs, and they're roughly the same time. And I don't know how much time I have left. But I think I'm pretty much done, and I'm willing to take questions if I have. Or we can just go into Circle Stark and prove. I don't know how much time I have left. What? I have 5 more minutes. Okay, so I can either sing a song or I can just answer questions. But I'd rather answer questions.
Okay. Thank you, Eli. This is great. Was there more you wanted to present, or you presented everything?
There's no more to say, but I would love to answer questions.
Okay, let's take some questions.
Hi, thanks a lot for your talk. And my question is regarding how well this plays with Bitcoin. First of all, it's impressive that you've even considered building it for Bitcoin, given how weak it is. And I have kind of 2 questions. One is, how is that even possible that you can actually do that on Bitcoin? And the second is, did you at all think about Bitcoin when you were defining Circle Stark?
Oh, terrific questions. Okay. How is it exactly possible? I'm going to give a lot of credit to the brilliant researchers working on OpCat, people like Wei-King Chen from L2 Iterative, and on our team we have a lot of very smart researchers looking into how to put it on Bitcoin. It's darn hard because Bitcoin, it's like one of those scientific calculators. So with Opcat, what you can do is like a concatenation of strings, which allows you to do, check things like Merkle paths and deal with state. That's the extent of what I can explain about it, but it's very messy. I will say that the demo has already, settled a Stwo Stark for a very simple statement. I think it's the Fibonacci sequence of like, 100 numbers or so. But it shows the path, yeah. And then, if we imagine that this will, no, so it's not that we said, we want to put it on Bitcoin, so we'll go to 32-bit field and so on. No. Since we founded StarkWare 6 years ago, it always pained me immensely that we are burdened with working with large fields, because we knew that just over small fields, things will be extremely, much faster. But we did it because the main cost on Ethereum is basically verification, and verification costs the same for any integer size, and it was simpler to go with it. So that was the reason we moved now to smaller fields, and it happened to be a very fortunate coincidence that also helps us with Bitcoin.
Great, thank you.
So if GPUs go to if the GPU goes to 64-bit field, presumably you'll need a different prover. Is that going to make things better or worse?
I think over 60, okay, it really depends how fast are your basic operations over the 64-bit field. If they are just as fast as 32-bit, I would guess that you probably are better off with a 64-bit field, just because, but I think it's unreasonable that 64 will be as fast as 32. But if it is, yeah, then maybe you want to go with 64.
Yeah.
How large are the proofs?
So the current proofs here at the current state are very large because we're not optimizing right now. Well, when I mean very large, I would say, let's say 100 kilobytes. But right now, so we're optimizing right now for performance, and there are all these parameters that we can tweak. For instance, the blow-up factor, stuff like that. Right now, we're not dealing with that yet. But you could, I would say that you could parameterize it to be, at the worst case, it would be, let's say, 200 kilobytes. If you work really, really, really hard, which means the prover will run a lot more time, you can probably make them be as small as, let's say, 20 to 40 kilobytes, but the prover will run a lot. And then you can, of course, sandwich, at the bottom of the layer, you could use like these large proofs and then recursively prove them. At the very end, you're going to use some very small proof. This is going to be highly relevant with respect to Bitcoin, because with Bitcoin, not only do you want to put extremely small proofs, you also want to use an interactive Stark. You don't want to use it like in a snark mode, a one-shot thing. You get 80 bits of grinding per block of Bitcoin, and you can use those 80 bits of grinding in order to use a smaller number of queries and reduce the cost. So, every setting will be different. Yeah. Any other questions?
Yeah, I have one. I'm thinking about how this sort of proof system design space changes as we shift targets from CPU to GPU. In listening to Daniel's talk yesterday, he described M31 as the end game for CPU-based provers. And I'm hearing from you that Circle Starks are fast on both CPU and GPU, but I'm curious, I guess, both is it clear that Circle Starks are actually better for GPU-based provers? And also, do you have a particular focus between, are you optimizing your design for CPUs or GPUs when it comes to conflicts between the two?
I don't know I'll say in what senses do I not know the answer yet. First of all, we just started exploring the GPU aspect of it. I'm not a sufficient expert on GPU hardware to say where it would lead. I do know that, again, just because the GPUs don't support binary field operations, then probably you want to use, prime fields. Now, whether M31 with respect to, I heard from, I think, Jeremy Brussel and the Risk Zero team, that on GPUs, you don't get that much better. Baby Bear and M31 pretty much are the same on GPUs. I don't know if you get any savings. I would say that the design, okay, what I feel very confident about is that the design space for extremely, for the fastest provers, it's going to be all focused on small fields. How small the fields are going to be, I don't know if it's going to be 32, smaller size, or maybe all the way up to 64 if the hardware supports it, but definitely it's going to be focused on the small field stuff. Now, what I'm much less confident about is, what is the right mixture of GKRs and logups and lookups and the usage of air and what degrees. And then there's this huge parameter space, right? Are you optimizing for proof size or on which architecture? That I have, we're just, but it's all going to be, in terms of the very performant Starks, it's all going to be a small field.
Yeah.
If you want very small proof size, like 1K and below, you're still going to, we don't know how to do that unless you use like a pairing-based snark. So
and you said the GPU numbers that you were talking about are like released online today, or?
So the Blake 2 thing is there, and there'll be a blog explaining the arithmetization next week. The GPU probably, Andrew, is the GPU, it's probably not released, right? No, the GPU is not released, so you'll have to trust us. Hopefully we'll get it released soon.
Thanks, Eli.
Amazing. All right. Very excellent talk. Thank you, Eli. This was fantastic.